An enhancement of data security in cloud computing with an implementation of a two-level cryptographic technique using AES and ECC algorithm. Cloud computing has expanded significantly in recent years to become one of the major research areas. Aside its numerous benefits, it is also encompassed with challenges, most importantly with the issue of data security. In essence, the paper presents an improved technique in ensuring data security in cloud computing. This study proposes an enhanced data security model using a two-level cryptographic technique: symmetric, AES, and asymmetric, ECC, cryptographic technique. This new technique seeks to pass data through the cloud space in a secure way, preventing third parties or intruders from accessing or making meaningful information out of the data being passed through the cloud space. The paper considered the time taken to perform cryptographic operations enhance the security of data against intruders, denying them from having access to the real data, enabling the confidentiality integrity of the data, increasing level of speed with the use of smaller keys of ECC in the cryptographic process, and increasing the trust level of usage of the cloud computing platform. Keywords: cloud computing, AES, ECC. Introduction. Cloud computing, CC, has expanded significantly in recent years to become one of the many research areas. CC is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. 1. The term describes an improved technology that ignores the storage of data onto traditional data centers but leverages on external distributed data centers to store, process and access data. The cloud is divided into several models based on the type of services, SaaS, PaaS, and IaaS, offered to its clients. Cloud services may be used in a private, public, community or hybrid as deployment models. Many individuals and companies now leverage on the use of cloud computing, becoming the necessary medium for storage, easy accessibility, and preventing of data loss as compared to traditional computing. However, knowing that security cannot be 100% guaranteed, it is necessary to continuously find more secure ways in protecting the cloud environment from attacks and data breaches, as it is a rising concern raised by many users. Among many individuals and organizations, data is a valued asset to them. A successful theft of 143 million client accounts from Equifax, which is a customer credit reporting agency, a cybercrime with shocking outcomes due to the kind of personally recognizable information attained, was one of the many important data breaches that impacted end users in the year 2017 too. Therefore, our main objective is to find a better means of securing data to minimize the loss and leakage of information, thereby improving the confidentiality, integrity of data passing through the cloud space, and increasing the level of trust of users. In that regard, we propose an enhanced two-level cryptographic conceptual framework that is implemented in the work. A good cause for this study rests on the skill or combination of algorithms of the system proposed. Literature survey. A considerable amount of literature on cloud security and privacy has been published by several researchers. This phase of the paper presents some of these reviews on data security on CC. In 2015, Abbas and Mariusz proposed a work that provided a reliable, efficient, and scalable method for improving CC data storage security. Their approach encompassed three main aspects of using private key generator, package, trusted cloud, TC, and the user. In 2016, Abbas and Mariusz presented a new architecture in improving the security of data within CC. This involved the usage of a modified identity-based cryptography, MIBC, as well as the elliptic curve integrated encryption scheme, ECS, algorithm, which were the two encryption techniques used. The objective of their research was aimed at providing reliable, effective, and scalable methods for improving data security in the cloud. In 2016, Muthurajan and Narayanasamy examined how to improve the integrity and security of data transfer founded on the Schneer scheme built on the elliptic curve. The paper suggested a VM-based cloud model utilizing HCSA to eliminate unrelated content and avoid system duplication. The model involves two stages, the system model and the threat model analysis. In 2018, Smitanisha Mendonca aimed at developing a high-performance AES to further expand its prevalent application. The data sent from the user to the cloud is encrypted using AES algorithm. Therefore, request made to access the data must be decrypted at the user's end. The original text is not written on the cloud. A key managing server is installed to store the keys. The research suggests that this type of encryption means protects both the data and encryption keys. It was found that AES encryption algorithm has a minimum storage capacity as well as good efficiency without any flaw or restriction. In 2019, Kumari, et.al., based on several research made, proposed an ECC-built mutual authentication framework for secured communication. This model involved three phases: the setup phase, the extraction phase, and lastly the mutual authentication and session phase. It was observed that users authenticate each other and establishes a session key. Using the session key, participants can connect securely over the public communication network. Also, the protocol does not allow measurement of bilinear pairing, stressing that it makes the protocol in the communication domain very efficient. 6. Two-level cryptographic technique. The scope pertaining to this research is tailored to developing an enhanced protection of data using encryption, leveraging a two-level cryptographic technique. In this state we incorporate both usage of symmetric and asymmetric cryptography, AES, and ECC respectively. The target is to develop a model to enhance the protection of data in cloud employing cryptographic technique. This will provide a reliable, efficient, and scalable method for improving the security and safety of data passing through the cloud. Advanced Encryption Standard, AES. The symmetric key cryptography is established by Belgian cryptographers known as Joondeman and Vincent Rijman. Normally used for faster encrypting or decrypting of huge size of data. This is because there is no regeneration of another key but uses the same key for both its encrypting and decrypting process. The AES uses 128-bit, with 10 encryption rounds, 192-bit, with 12 encryption rounds, or 256-bit, with 14 encryption rounds, keys to encrypt 128-bit blocks of data. 7. It is proven to have an increased level of security, that comes with large key size, and can encrypt messages faster than the 3-8. The encryption with its decryption process involves the following systematic processes are, byte substitution, shift rows, mix columns, add round key and then the inverse of these processes in order to decrypt it. 1. Encryption process. In the course of the encryption process, each round is made up of the 4 sub-processes mentioned above. A. Byte substitution. The first modification of the AES encryption cipher is substituting data using a substitution table. The 16 input bytes are replaced by the fixed table which is the substitution box, S-box, and contains all likely combination of 8-bit order. The resultant new 16 bytes are arranged into a matrix of 4 columns and rows. 5. B. Shift rows. The second transformation shifts rows of data. Each row in a matrix produced from the byte is moved/changed to the left. Any of the entries that shifts off is reinserted to the right side. The first row remains as it is, and the next row is shifted by a byte which is situated to the left. Then the third row shifts 2 positions towards the left whereas the fourth row is shifted by 3 byte position towards the left. The resultant matrix then comprises of the same 16 bytes nonetheless at different positions. 5. C. Mix column. At this point, the third transformation mixes the columns. Each of the columns of 4 byte is then changed employing a special mathematical function of the Galois field, GF. The function takes the 4 bytes of one column by means of input and outputs 4 new bytes to replace the original column. The step is not done in the final round. 5. D. Add round key. The last transformation which is simple, that is carrying out exclusive OR operation on each column using a different section of an encryption key. The 16 bytes of the resulting matrix produced from the mix column stage are then considered to be 128 bits. At this stage, the 128-bit state is bitwise XORed with a 128-bit round key. The output is the cipher text if it is the last line. Else, the resultant 128 bits will be read as 16 bytes and will start another likely process of substitution. It is a column-wise operation between 4 bytes of state column, 1 word of round key. 5. 2. Decryption process. This involves the reverse or opposite of the encryption process until plain text or original data is gotten. A. Add round key. This has its own inverse function, which the round keys are selected in the reverse order. B. Inverse shift row. The inverse shift row works exactly the same way in the reverse order. The first row is kept so, then the others, second, third, and fourth row, is shifted by 1 byte, 2 bytes and 3 bytes position to the right respectively. C. Inverse byte substitution. This is done by using predefined substitution table identified as the inverse S-box. D. Inverse mix column. The transition in the reverse mix column is achieved by using polynomials of lower than 4 degrees over the Galois field, GF, 28 of which the elements of the state column are the coefficients. B. Elliptic curve cryptography, ECC. The ECC is a mathematical technique used to create encryption keys, secure digital signatures and more. It is used in making lesser, quicker, and more efficient cryptographic keys. In 1985, the ECC's usage has been suggested by Neil Koblitz and Victor Miller. 9. 1. The arithmetic of elliptic curve. ECC's main attraction is its ability to provide an equivalent security level but this time with much lesser key size as likened to the RSA cryptography. The elliptic curve equation can be defined by equating all its coefficient and variables taking within the set of integers and ranging from 1 to n1, performed by calculating the modulus. If using elliptic curve for cryptography, the coefficients and variables in a finite abelian group are restricted 10. Below is the equation for the ECC. Y2 mod p equals x3 plus x plus b, mod p. 2. Elliptic curve discrete logarithm problem. ECC is founded on the density of the elliptic curve discrete logarithm problem, Ecdhq. Suppose E is an elliptical curve over certain finite field fq and then p representing a point order n on E. The Ecdhq shall find the integer d on E. 1, n, 1, where there is such an integer. DLP doesn't look like Ecdhq, except the Ecdhq is even tougher than the DLP9. The notion of finite field is the important characteristic of the elliptic curve, giving a way of limiting values on the elliptic curve. 3. Security of elliptic curve cryptography. With the many asymmetric key cryptography techniques, the theory of elliptic curve proves that it can be used to generate easier, lesser, and more effective cryptographic keys. Using a 160 bits in ECC almost offers similar level of security against attacks as compared to 1024 bits in RSA11. Because of its key length, it is recommended for security applications whose electronic components, wireless devices, smart cards, PC cards, may have a reduced level of computational power. 9. The security of the algorithm depends on the difficulty in resolving. ECC generates smaller keys which eventually produces better performance as compared to others like the RSAs. ECC is more scalable compared to RSA, which gets more cumbersome as key expands and less vulnerable even to quantum computing, and since it's more of a new cryptographic technique as compared to the others. 12. Table I reasonable bit length. 9. C. The proposed model. In this model, the first level is tagged as first level security, where the data is at rest. Both the encryption and decryption of data is done via algorithm of AES. At second stage of security, tagged as second level security, uses the ECC algorithm. At this stage, the encrypted data is in transit across the cloud space. It uses ECC in generating digital signatures and encryption keys to allow for safe transit of the data across the cloud space. The ECC, a public key crypto system, is also used for key management and authentication. The figure below clearly shows the architecture of the proposed model. Proposed general conceptual two-level cryptographic diagram. Plain text file creation. A first-level cryptography using AES algorithm. At the first level, AES is used to encode the message. A sheer symmetric secret key is generated and known between the two parties or clients involved in the communication. The AES CRYPT is the tool used at this stage. The figure below shows how the encryption is done. Initial part of the first-level cryptographic process showing encrypting with AES. B key generation using the ECC algorithm. At this stage, the OpenSL tool is used in the cloud space. At the initial stage, the private keys are related, and public keys from these private keys are generated. ECC key generation using OpenSL. See elliptic curve Diffie, Hellman key exchange shared secret key generation. In generating the shared secret key, both public keys of the sender and receiver is first shared to the cloud. The shared secret key is a common key brought about by using the Ecdhq. Before performing the Ecdhq key exchange operation, the public keys of both users are shared on the cloud, which any user may have access to. Figure 8 shows how it is done. Public keys shared on the cloud space. In performing the Ecdhq key exchange operation, the private key of party A is paired with the public key of user B to produce shared key for party A, whereas the private key of party B together with public key of party A to produce the shared secret key for party B. Figure 9 shows how the shared key is produced. Ecdhq agreement protocol implementation. We continue by hashing the shared secret key, enabling it for authentication, in which a hash function is performed on the key. SHA-256 hash of shared secret key. After hashing the shared secret key, it is used together with the AES-256 to encrypt the ciphertext message earlier encrypted using the AES algorithm of the party's machine. The 4 is added to the key to essentially scramble the key to encrypt the data passing through the cloud space. This process is done in a way that the client or user at the other end knows the operation used to reverse the process at the time of decryption. Encrypting data in cloud. The elliptic curve digital signature algorithm, EXA, generation/signing. The EXA is a digital signature algorithm, uses derived keys from ECC. The ECC, having generated a pair of keys, public and private, for the parties involved in its encryption process, uses the private key to sign the message and authenticated or verified by the public key of the originator. To perform the message signing, the private key of sender together with a secured and common hashing algorithm known to the receiver is used. This has the property of irreversibility where it is almost impossible to determine the message from its digest. This has the property of irreversibility, collision resistance, and a high avalanche effect. Use of EXA to sign message. ECC decrypting in the cloud space. At this point, since the receiving client or user uses the same algorithm, it means that the for used in encrypting the data is only known to the receiver and will be used in decrypting data. ECC decryption of data in the cloud. FXA verification in cloud. In the simulation, the verification of message is proven to be right, indicating as verified OK. At the position when the right verification process is wrong, then the message doesn't get authenticated and therefore gives a flag, as seen in the below figure. Verification of signed message. Final stage of decryption using AES algorithm. Since the common AES key is known by both parties, the tool script is used again on the party B side to decrypt the ciphered data to its clear text. The figure below shows how the final stage of decryption is done and the message obtained and displayed for the party to read. Final stage of decryption using AES algorithm. Calculation of the encryption and decryption time. The encryption and decryption time are the time it takes to encrypt and decrypt data in the cloud respectively. Encryption time and decryption time in the cloud space. The simulation recorded different times during the encryption and decryption processes, and this was due to these factors: load on central processing unit, CPU, memory, and hard disk giving different output times. The outputs produced as shown in figure 16 are indicated as real, user and SYS. Real time, the real time between initiation and termination of the program including other processes that may be running at the background. User time, the CPU time used in the user mode is known as the user. It uses the user space instead of the kernels. SYS time, the SYS time refers to the time spent within the process in the kernel. This time is spent in the system calls within the kernel. Discussions of findings. The Ecdhq key exchange for producing shared key makes it totally impossible for third parties or attackers to produce same key in decrypting the data. The 4 also adds up to the increasing level of security, which makes it even harder for intruders to get to decrypt the data. Moreover, data is encrypted twice, that is first on the client's machine and later in the cloud. All this proves the enhancement of the security of data, hence the confidentiality. By implementing ECC, the smaller keys produce an equivalent level of encryption as compared to the other asymmetric encryption, even at a faster rate, showing the enhancement of the speed and security of data. The integrity of the data is also maintained by the usage of the EXA, which allows for the integrity check of the data. The trust level is enhanced from the end user's perspective as well. This is because the user gets to encode the data even before passing through the cloud for further encryption. This will inform users of the privacy of their data and encourage more users to patronize the usage of cloud services. Lastly, it is found that the load on both CPU, memory, and disk determines the time it takes to encrypt and decrypt data. Conclusion. This paper presented a 2-level cryptographic technique and a model for the enhancement of data security in cloud computing. The model employs the use of both symmetric and asymmetric encryption algorithm, AES and ECC, to enhance the security of data against intruders or third parties, denying them from having access to the real data, enabling confidentiality, integrity of the data, time taken to perform cryptographic operations, and improving the trust level of users of CC and increasing level of speed with the use of smaller keys of ECC in the cryptographic process.